Hello everybody. In the last lecture, we already started talking about CNNs for semantic segmentation. In this lecture, we will continue that discussion. From the discussion in the last lecture, we already recall that the early CNNs were classification oriented. However, the semantic segmentation, this is different from classification in the sense that for semantic segmentation, we require dense outputs. That's why the classification oriented CNNs needed some modification for dense output or for pixel wise prediction. And this was achieved by designing fully convolutional networks. So we'll go into the more details of this. So what's the motivation behind the FCN, fully convolutional network? To achieve pixel-wise prediction, it works by removing the fully connected layers and thus by preserving spatial feature maps. So if we had the fully connected layers, you'd remember from our discussion that we are losing the spatial information, whereas by removing the fully connected layers, we are preserving the spatial feature maps. Whereas, of course, we are still downsampling the information. How to handle that will be coming soon. However, by removing the fully connected layers with this design, we are now able to handle arbitrary size images, and we would be in the FCN, we would be able to learn the segmentation end to end. How? Let us come to that soon. The key idea of the FCN, as we have already mentioned, that we have to replace the fully connected layers with what? With convolution itself, or rather a version of the convolution which we are going to discuss soon. The key idea is also to maintain the spatial correspondence, and so spatial correspondence is maintained, of course, like if we had started with H cross W images and now we have a feature map which has the spatial dimension H dash cross W dash, where this H dash and W dash, they are less than H and W. However, they are not like the same size, right? So we need to get back also the same size as the input, that is H and W. So we need to upsample the low resolution feature maps somehow. And we need to get a class coarse at this pixel level. Then we need to train the entire network end to end, as we have already mentioned before. Now, with this information about the key idea of the FCN, let us go forward and let us try to understand again a bit pictorially what's happening here. Given an input, so we can see the input here. Let's say this is a 3-channel image. Of course, from the drawing here, maybe it's not that clear. However, you can assume it to be 3-channel. Of course, it could be some other channel as well. Especially in the case of the Earth observation, it could be, let's say, 4-channel, 13 channels, or any other value. Okay. So given this, what's happening using the convolutional layers, we are slowly in the spatial dimension we are reducing the dimension, right? If we started with the 224 cross 224 images, maybe this is 112 cross 112, maybe this is 56 cross 56, could be some other value as well. Whereas generally in the feature dimension, so if we started with these 3 channel images, so this was 3, maybe this was a higher value, let's say 64, let's say this was 128. And at some point, if it was a network for classification, at some point we had the fully connected layer here, 1 or more, which we don't have right now, since we have made like a fully convolutional version of this. Now, this is not all. We also need to obtain the same number of channels as our output class, right? So this could be, in some sense, I mean, if that was all our goal, think a bit about this. Take a few seconds, pause, that how could you obtain this if our goal was to not really like actually getting the spatial dimension back. Our goal was just to get the same number of channels as the output class. So there we could have applied also just 1 cross 1 convolution, right? However, of course, our goal is to obtain an output which has the same spatial dimension as our input image, right? So if we started with 224 cross 224 image, we would like to obtain an output which has also the same spatial dimension, that is 224 cross 224. So there rises a question that, okay, how we can do that? And there comes the upsampling. What is happening here is that the CNN downsampling, this is reducing the resolution, the spatial resolution. However, to emphasize again, the segmentation requires full size prediction, and thus we need some form of upsampling here that can restore the spatial dimension. And for this purpose, what is generally used is something called transposed convolution. So we have already talked about convolution. Now we're talking about transposed convolution. Okay, so let us see some example to understand how it would work. Here, think about an input. Okay, so 0, 1, 2, 3, and we are talking about a transposed convolution with a stride of 2, and think that we are processing with this kernel. So the particular example we took again, it's 0, 1, 2, 3. Okay, so now think about this. Given this input and given this kernel, think about taking these multiplications. Okay, 0, 1, 2, 3, you are multiplying with 0, you are multiplying with 1, you are multiplying with 2, you are multiplying with 3. Okay, so at first you are getting this 0, 0, 0, 0, and remaining increase you can think of as 0, added with, multiplied with 1, 0, 1, 2, 3, and all the other entries you can think as 0, added with, multiplied by 2, and all the other entries as 0, and multiplied by 3 and all the other entries as 0. And you add these 4 matrices, and what you get is this 4 cross 4 matrix: 0, 0, 0, 1, 0, 0, 2, 3, 0, 2, 0, 3, 4, 6, 6, 9, right? So we started with 2 cross 2 input, and now what we have is 4 cross 4. So I would suggest that you can experiment a bit yourself with the transpose convolution to learn more about this. And for this purpose, you can use this particular code snippet, which you can again code yourself in Python. And you see the input. So this is the input 0, 1, 2, 3. So this is the same as the input that I just showed right now, right? And here in this code, what I'm taking is, I'm taking one kernel 0, 1, 2, 3. So this is the same kernel as the one that we just saw. Here we are also taking another kernel, kernel 2, 4, 1, 2, 3. Okay, so this is a different kernel. And now what we are doing, we are taking this transpose convolution with respect to the kernel 1 and with respect to the kernel 2. Okay, and we are printing the output both times. So you can go through this simple exercise. So one time you are expected to see the same output that we already saw before. However, the second kernel is a different one, right? So for the second kernel, you would see a different output. So you can already compute this on paper before, like running this code. And then you can compare the output that you are getting from this code with what you would have obtained on paper. Now, considering that we already have this tool or layer, whichever we want to call this, that is enabling us to do upsampling, we can now get a network which can now actually give us the spatial dimension, our spatial size, desired spatial size back, right? So this now completes our design of fully convolutional network. What are some of the advantages of the fully convolutional network? So this is end-to-end trainable. This is enabling us for efficient dense prediction. We can work with arbitrary image sizes. And in a way, we can think this as a foundation for the later methods. So the later methods that we'll study, one of them we'll study in this lecture itself, and some of them will come later in this course. The FCN is working as a foundation for these later methods. So let us think about how do you train FCN, right? A pseudo algorithm for this. This is very straightforward. Given the input image, this enters the network. The convolutional encoders, these are extracting the feature map. And convolutional encoder, which has the pooling layers, it's also, so this progressively also reducing the spatial resolutions. So this part is quite similar to what we also saw for the CNNs designed for classification purpose, right? Now, the later part where the difference is there from like the classification type network, which we already discussed in today's lecture, this is coming here, right? In the second part, so for making it clearly identifiable, I have put two different red arrows. So you can now focus on the second part, second red arrow, where the upsampling is happening, and this is restoring the spatial dimension. Finally, we can compute pixel-wise loss, which can then be used to update the network parameters. So for such a network, like something which is very close to FCN, I would refer you to this particular paper, Dense Semantic Labeling of Subdecimeter Resolution Images with Convolutional Neural Networks from 2017, which more or less follows the FCN, the vanilla FCN version, whereas there are, of course, many work in the earth observation for semantic segmentation, where some kind of modification are used. And we will subsequently into this lecture and also in the other lectures will come to these modifications. However, for one of the early works on semantic segmentation, deep learning based or CNN based semantic segmentation for earth observation, one could refer to this particular paper. Okay, so with this background, now let us think a bit about how some of the possible strategies or choices can be very important when we are working for semantic segmentation. So one very important question here is the sampling strategy, because what happens is that semantic classes, especially when you're talking about earth observation, the semantic classes are often highly balanced. Think about an urban class. There, it's quite expected that, let's say, the buildings could be much more frequent than, let's say, the vehicles, right? The vehicles, they will be smaller in size, and if you take like a particular image, let's say 224 cross 224, the number of pixels that actually belongs to vehicles, that might be much less. And accordingly, like for other applications also, this is quite true. Some of the semantic segmentation tasks at the end is like binary semantic segmentation. Like, let's say we are talking about flood segmentation. So there again, depending how we design the data set, it could also be the case that the floods, that is very rare, but often it happens. Okay, since we are designing a data set for flood, we end up oversampling in the during dataset creation itself the scenes which has flood, and this creates opposite scenario where actually like the flood pixels are much more frequent than the non-flood pixels. And this kind of imbalance in the dataset, this needs to be carefully accounted for when we are designing the model or designing the loss function, or how we are sampling the data itself. We can, depending on the class frequencies, we can sample some data more, some data less frequently, some particular class more frequently, some particular class less frequently. Now, also, another very important aspect here to keep in mind is the ground truth data preparation. As very evident that most of the time we will be using human annotators to label for our particular downstream application, right? And human annotators to label each pixel, this will be a time-consuming process. Furthermore, the fine boundaries. So let's say like there is a grass court and then there is a road beside it. So such fine boundaries, right? Boundaries between such objects, this can be like very time-consuming to, or very challenging to label also. And this means it's quite expensive to create large data sets, expensive in the terms of time, expensive in the terms of also like if you even convert actually in like rupees, like okay, how much rupees we need, how much currency we'll need, that will also be expensive, because if it is challenging, of course, if you're hiring annotators will charge you more, right? And they will also need, like, let's say they charge per hour and they will need more time, right? So automatically it's also expensive in the terms of the annotation money as well. Weak supervision is often a potential solution, and weak supervision is a quite active research area here. So there are, like, standing in 2026 today, many times there are some potential very effective weak supervision strategies available. However, we'll discuss them at later part of this course. Also, to talk a bit about some of the potential evaluation metrics. So we have pixel accuracy, we have intersection over union, which can then be converted into mean IOU. We can also have die-score. So I will go a bit more details into the intersection over union. The intersection over union, this measures overlap between the prediction and ground truth. Generally, we'll compute this independently for each class. This is penalizing, of course, the false positives and also the false negatives. And then the mean IOU can be computed as average over the classes. Okay, now that what we have done, we in this lecture we understood the FCN architecture itself. Okay, how this works. Okay, how we have the convolutional layers and then the transverse convolutional layers, and we are getting back the same spatial dimension. We thought a bit about what would be the training recipe, and we thought a bit also about some of the potential issues with this, like, okay, how the data set imbalance can impact and what can be the potential evaluation metrics and such things, right? Now, let us go back again to our discussion of architecture. So here, the question that we would like to ask ourselves is that, okay, we are for sure getting back the same spatial dimension. However, remember that using the convolutional layers, we were slowly losing the spatial information to some extent, right? Like we were downsampling in the spatial dimension, and we were coarsening information in that dimension. So does that mean just using transverse convolution, this will enable us to get back that information? The answer is probably no, right? What is lost is usually lost. You cannot just get back, right, that information. So, is it the case that what is lost is really lost, or is there some kind of mechanism that we can devise to get back that information? That is the question that we are posing to ourselves. Can we recover it back to some extent? And there comes this architecture, probably the most popular architecture for semantic segmentation, that is UNet. What we see here, this is a very simplified picture. What we see here is that, okay, we have the encoder, we have the decoder, and in between these encoders and decoders, I have added some connection. What kind of connections are these? These are skip connections. So these skip connections, we are claiming that, okay, this will enable us to restore some of the information that we had lost when we were coarsening in the spatial dimension using the convolution layers. Okay, so let us try to understand it a bit better. So what does the unit consist of? This consists of encoder, the contracting path, which extracts semantic features, which reduces the spatial resolution and increases the feature depth, right? So this is not so much different from just trivial FCN. And we have the decoder, the expanding path, which is restoring the spatial resolution. This is producing dense pixel-wise predictions. And this is what, in addition, we are doing. We have the skip connections. The skip connections are transferred in fine-grained spatial information from the encoder to the decoder. And in this way, this is helping to recover the object boundaries. Let us see a bit more in details. So the unit decoder, what's the purpose of the decoder? To recover the spatial resolution, to generate dense segmentation maps, to define object boundaries. And there, again, the question, what is lost, how to get it back. So here, let us just give a bit this example of the human dreams, right? Like in human dreams, often information stored in our brain from long past is, like arranged back in our human dreams. This is very interesting, like you can read about human dreams. I mean, this is of course not related to our subject, but this will help you to understand. In my understanding, this will help you to understand the unit better in some way. So the unit skip connections, how is it helping? This is helping us to get better localization, sharper segmentation marks, also improve gradient flow during the training. So let us look a bit in the code. This will help us to understand a bit better. So given at this point of time, we are trying to design an encoder. So we had just one encoder like block here, right? So let us add more blocks, more encoder blocks. Okay, so we have added one more encoder block, and in this way we can add a number of blocks. So let's say we have added like such 4 blocks, right? And a bottleneck. Okay, so this completes our encoder part. Now let us do in this way. Let us add decoder to this. The decoder will have skip connection from the encoder, right? So the first block of decoder will have skip connection from which block in the encoder? Just take a pause for a few seconds. Think about this before moving forward, okay? Before seeing the answer yourself. Okay, think about this. Okay. So let us see it. The first decoder block, okay, this is taking the input from the encoder 4. Similarly, we can keep going forward. The next and the next, like this, we keep on adding the decoder blocks, okay, and this is taking the input from the encoder 3. The next one is taking the input from the encoder 2. The next one is taking input from the encoder or the skip connection from the encoder 1, right? Finally, we'll be getting the output mask over here. We can also think a bit about the spatial dimension. How, if we started with, let's say, a 256 cross 256 image, how the spatial dimension will evolve, going fast through the encoder. 256 cross 256 was 64, and then the downsampling is happening with the pooling layer, and slowly the similar phenomenon keeps on happening through the encoder. And when we go now to the decoder, we will be getting back our spatial dimension, and finally we get back the 256 cross 256 input, the same spatial dimension, and into the number of classes. So here we are ending our discussion on semantic segmentation for now. However, we keep coming back to semantic segmentation in different contexts. Thank you.